Hi all, welcome to the next video of the video lecture series for the subject compressible fluid flow. In the previous video, we have discussed what is the importance of compressible fluid flow in engineering and also what is the major difference between a compressible fluid flow and an incompressible fluid flow. And also for the study of the compressible fluid flow, we require certain concepts, certain fundamental concepts from our previously studied subjects like fluid mechanics, engineering mechanics, and thermodynamics. So certain laws will be coming again from those subjects. And we have discussed in detail about certain applications, certain direct applications of the subject compressible fluid flow. Some of the examples were high-speed aerodynamics, rocket propulsion, turbo compressors, steam and gas turbines. And we have started the syllabus of the subject with the concept called continuum concept, which will be required in the beginning of every mechanics subjects like solid mechanics, fluid mechanics, engineering mechanics, whatever mechanics is considered, we require this concept, continuum concept. So we have started the concept. We have discussed in detail about what is continuum and what is the importance of using this concept in our compressible fluid flow also. And like we have said, in most of the engineering problems, the behavior of the individual molecules in a system is of little importance. That means in most of the fluids and other substances, they are made up of atoms and molecules. But if you are considering the atoms and molecules and the structure of them in our compressible fluid flow problem, our solution will be the solution of the problem will be very complex. It will take so much time and so much resource. So we need to somehow simplify the problem. That can be done by using this continuum approach, by this continuum concept. So basically in this continuum concept, we will consider the substance as a continuous matter instead of atoms and molecules. By that way, we can describe the matter by some gross behavior of the substance instead of describing about the atoms and molecules. So the problem will be very much simple. The complexity of the problem will be decreased. We can solve it by using some limited resources. Okay. So we can explain the continuum concept with the help of an example. Consider a container filled with oxygen gas at atmospheric conditions. So the diameter of the oxygen molecule is about 3 into 10 raised to minus 10 meter, and its mass is 5.3 into 10 raised to minus 26 kilograms. You do not need to memorize these values. This is just for the sake of example only, for the sake of explanation only. For exam point of view, you just need to need to explain the procedure. Okay, no value is required. Okay, so oxygen molecule diameter is 3 into 10 raised to minus 10 meter. Now, you will consider the mean free path of oxygen at atmospheric conditions. The mean free path at 1 atmospheric pressure and 20 degrees Celsius is 6.3 into 10 raised to minus 8. Now, what is mean free path? Actually, mean free path, uh, let us consider a diagram. Here, 3 oxygen molecules are shown. And this is a gas. Oxygen is basically a gas. So these molecules will collide. And if you are considering multiple collisions, the distance traveled by a particular molecule from one collision to the corresponding collision. That means if you are considering 2 collisions, the distance traveled by a molecule from the first collision to the second collision, if you are recording that distance, therefore we can record the distance like that for all the collisions. For all the collisions, we can record the distance like that, the path like that. And if we are taking the average value of all those distances, all those path of the molecules before between two consecutive collisions, that average value is called mean free path. Okay, so in this case, in the case of oxygen, the mean free path is 6.3 into 10 raised to minus 8 meter, which will be 200 times greater than its diameter. So if the oxygen molecule is this much large, then the distance between, if you are considering the mean free path as an average distance between the molecules, the distance between two molecules will be 200 times of its diameter. Okay, so there will be a large gap between these molecules. So there are about 2.5 into 10 raised to 16 molecules of oxygen in a tiny volume of 1 millimeter cube at 1 atmospheric pressure at 20 degrees Celsius. So that means if the mean free path is very large, if you are considering a point of interest in between these molecules, if you are considering a system or control volume between these two molecules, in a space between these molecules, there will not be any oxygen molecules in that control volume. Understood? So we cannot analyze or study about this system by using this control volume approach in this case, because the mean free path is very large. Despite the large gaps between the molecules, a substance can be treated as a continuum because of the very large number of molecules, even in extremely small volume. So this limitation can be rectified by using the continuum concept. In continuum concept, this gaps will not be considered. Okay, instead of gaps, in continuum concept, the control volume will be completely filled with oxygen molecules. There will not be any gaps. That is the main difference between this molecular approach and the continuum approach. That is what is explained here. So we can distinguish between these two cases by the help of some diagrams. So the actual material is shown here. The molecules are arranged in a systematic and regular manner, so that there will be gaps between them. But in ideal material is not realistic. It is not it is actually ideal. Okay, that means it is not existing in the nature. It is a concept actually. Because of that, because of it is a concept and assumption, there will not be any gaps between the molecules. So this considered volume will be completely filled with oxygen molecules, such that there will not be any gaps between the molecules. This ideal material is an example for the continuum concept. So we are actually assuming our problem or our system to be ideal in the continuum approach. That is the main difference. Now, how can we distinguish this ideal material, and what is the extent up to which we can consider the material as ideal or actual? That we can explain by the help of a number called Knudsen number. Knudsen number is just like our Reynolds number. Just think about Reynolds number. Reynolds number is a non-dimensional number which is used to distinguish between types of flows. We can distinguish the flow we can classify the flow like laminar flow, turbulent flow, transition flow on the basis of the value of the Reynolds number. Just like that, we can use a number called a Knudsen number, which is used to distinguish between actual material or the molecular approach and the continuum approach. So Knudsen number, denoted by Kn, it is actually the ratio of the mean free path Lm to any characteristic linear dimension capital L. This any characteristic linear dimension, which means it can be the breadth of this area or the height of this volume or the length of this volume. Any characteristic linear dimension can be taken. So if you are considering the equation, Kn is equal to mean free path, that is L suffix m divided by L, and there is a range. If the value is less than 0.01, the continuum approach is valid. So let us look at this value 0.01. That means the numerator value is very smaller than the denominator value. That means mean free path is very, very small than the characteristic length, linear dimension. Okay. That means the gaps will be very, very small. Even if there are gaps between the molecules, if the Knudsen number is less than 0.01, that gaps will be very, very small, such that we can consider the material as a continuous substance like continuum. So that is a condition for the continuum approach, for the validity of the continuum approach. The Knudsen number should be less than 0.01. Now let us look into the other side. When the Knudsen number is greater than 0.01, when it is getting greater than this value, this mean free path value will be increasing. That means the gaps between the molecules will also be increasing. When the gaps increases, we cannot use the continuum concept in that situation. Okay, so there is a limitation for the continuum concept. That limitation is expressed by this Knudsen number value. Okay, now let us discuss in detail about the limitation for the continuum concept. It is not valid under the following conditions. The first condition, if the mean free path of the molecule is comparable with some characteristic length or the distance in the system, just like we have discussed now. This is the case of increasing mean free path. If the value of the Lm in the Knudsen number equation, if it is comparable to the L value, which is the characteristic length value, or we can simply say that if the Knudsen number value is greater than 0.01, we cannot use the continuum concept. That means the mean free path of the molecule is comparable with the characteristic length value. Similarly, if the average time between the molecular collision is large, that can also be explained in association with the mean free path. See, mean free path, we can say that mean free path is actually the average distance between two molecules, or average distance between two consecutive collisions. Like that, we can say the average time between the molecular collision. If you are taking the time between the consecutive collision, and if you are taking all the time between the collisions, and we are taking the average value, and if the time is large, that also means the distance is large. The molecule will take more time to get to travel and to collide with other molecules. So if the average time increases, that means mean free path also increases. Okay. So in this case also, continuum concept, the Knudsen number value will be greater than 0.01, and the continuum concept cannot be applied. So the assumption of the continuum permits the use of macroscopic approach. Since we are not dealing with atoms and molecules, we do not have to deal with the microscopic nature of the substance. So here in the continuum concept, we will be considering the macroscopic approach of the given problem. In this approach, continuum is valid. And in case of molecular analysis or molecular dynamics, in the case of atoms and molecules, if the gaps are very large, such that the Knudsen number value is greater than 0.01, we cannot use continuum concept. In that case, we will use a concept or a study called molecular analysis or molecular dynamics. Okay. In that case, the microscopic approach is used. Okay. So in microscopic approach, continuum is not valid. This is very important. It has been asked for several exams. So just keep in mind that this is a very important topic. And we have to go through certain important relations, thermodynamic relations, and we will be discussing those relations in the next class. Thank you.